Okay, we're back and we're here to start a Unit 1 ray tracing field amplitudes. And this is part of our lecture series on geometrical optics. The first video we talked about the ray tracing equation and how we can use high frequencies to approximate the Helmholtz wave equation. And then we talked about the iconal equation and how do you physically trace waves? What is the mathematical meaning of that? One of the key outcomes to that is the famous iconal equation where the gradient of your iconal is equal to the index of refraction, approximately, under certain circumstances. Then over here, this was the solution we started with. The iconal, the phase function is here. It's a function of three-dimensional space. And the equiphase surfaces really describe the shape of how we think of rays. So if you set that equal to a constant for different constant values, C1, C2, C3, you get different shapes in space, and the rays trace out those waves perpendicular to those surfaces. Now, of course, we learned that in free space, rays are straight, and that the gradient of the iconal is a constant. The magnitude of the gradient of the iconal, and we usually use double lines to denote magnitude in this class, since the gradient of S is a vector. Now, we haven't said anything about the amplitude here, and that's as much a part of the solution as the physical tracing of the waves. So we are going to have to go back now and figure out how to calculate this from classical geometrical optics. And that's really the theme of the lecture for today. So recall that we had two equations. When we plugged that theoretical solution for fields that involved amplitudes and phase functions, iconal functions, we had this first term, which is all the real stuff, and the second term, which is all the imaginary stuff. We got the iconal equation by approximating this first term using high frequencies and saying, well, this has to be equal to 0 since the whole complex equation is equal to 0. Now we're going to figure out the amplitudes by saying this part also has to be 0, which means that the dot product of the gradient of the electric field dotted into the gradient of the iconal function must be equal to this quantity, the amplitude times the Laplacian. We'll call that the Laplacian, at least in Cartesian coordinates, is just really equal to the divergence of the gradient, which is like multiplying by second derivative, partial derivative with respect to x, plus second partial derivative with respect to y, plus second partial derivative with respect to z. Now, we are going to apply this identity here to change things. If we've got an amplitude function that's a function of 3D space, and a phase function that's also a function of 3D space, if I take the gradient of the iconal, and I come over here and I take the gradient of how the field amplitude changes in space, however that might look like, I can rewrite this as the magnitude of the gradient of the iconal multiplied by the derivative of the E field along the path direction S. Remember, in this equation, S is the distance along the ray that you travel. So if I travel a certain distance S, I'm going to change my E field. And if I take that portion, that basically the change along S, and multiply that by the magnitude of my iconal gradient, I get the same thing as the dot product. It's really just a projection onto the direction of the ray travel, that using that vector calculus identity. So, moving right along, we can rewrite this equation as dE, and you'll note, if you didn't recall that from the previous lecture, that we're using that diamond subscript to denote independence of polarization. This is a scalar field, and if you start out with vertical polarization, you leave it as a vertical polarization in all of these examples. If you start out with circular, you leave it at circular. We're assuming we have an isotropic medium, so in most problems it's pretty straightforward to carry the polarization along for the ride. Now, over here we've got dE, ds. We're going to leave the dE over here and take this and divide it into there. So that gives us this term here. Derivative of E, dE over E. Here, we're going to take the rest of the iconal magnitude of the gradient and ds and put it over here. So now we've got all of our phase function terms on this side and all of our field amplitudes terms on this side, and we're going to integrate these. We're going to integrate these along the ray path. So recall, we had iconal functions. S is the distance from some starting point on a wavefront, marching it forward. And so we're going to integrate this from an initial value of E S naught to a point of observation value E diamond S. And then on the other side, we're just integrating from S naught to S naught plus S. And I always like to put a accent point, little prime, on my variables of spatial integration to distinguish them from the point of observation, which is what we're evaluating this with respect to. This is not a very difficult form on this side to evaluate. This, of course, is log of the field amplitude, and I've got to evaluate that from E S naught to E evaluated at S along array. And one of the things I'm going to do, I'm going to take this 2, move it over to here. It's in the denominator on the right hand side. It's a constant, so I can just take it out and put it in the front here, which is really the same as squaring this, which, if I evaluate this fully through, becomes the log of E squared of S over E, and really S naught plus S, because S is going to be measured from my starting point. And so we're left with this equation here. Here's my starting field. Here's my ending field, s units later down the ray. And then I've got this term that I've got to deal with. And this term actually has a very special meaning. As we're going to find, this is something called Gaussian curvature. And we'll talk about how to calculate that. But as you can see, this is relating the starting point of field amplitude, which is squared, which we know is proportional to power. And we have power over here too, because we have a field strength squared. So in a way, what we're going to find is that this is really almost a statement of conservation of power. Rays carry power, and that power is conserved, we're going to find, as the ray spreads out. The power density diminishes. Okay. So, what is Gaussian curvature? So here's a diagram here in 2 dimensions. Let's say I have a starting wavefront. We'll call that point A here. We're tracing a ray. We find that the gradient of the iconal function when we trace the ray follows this path over to here. And we want to evaluate the new field amplitude at point B. Geometrically, Gaussian curvature is very easy to figure out. It's basically the curvature point. You start from your initial point, and if you backtrace the ray in space, and you move just a little bit above or below, here I show a slightly larger displacement just to make the figure a little bit more visually easier to interpret, so that everything's not jumbled around A. But there should be a point that if you go a little bit above and a little bit below, and you trace rays along those surfaces, those should intersect at some intersection point back here. In other words, there should be a radius of curvature at that point, which in this diagram is rho sub 1. Now, in 3-dimensional space, our surfaces have curvature in multiple directions. And if you pick the orthogonal direction, in this case, this horizontal area, I can do the exact same exercise. I can basically trace back my ray backwards, as infinitely long as it takes. And I can do the same with a ray that's a little bit to the right and a little bit to the left here. And that intersection point over here, with just small displacements, denotes my radius of curvature rho sub 2. And of course, these don't have to necessarily be the same value. They are for a spherical wave, but in the general case, these could take on any general value that conforms to the surface. And so, the Gaussian curvature, the way that we define it, with this kappa GA, Gaussian curvature at point A, is 1 over the radius of curvature, the radii of curvature, in 2 principal orthogonal directions. That's how we define it. 1 over rho sub 1, 1 over rho sub 2. And of course, if we ray trace the next phase front here, what we find is the Gaussian curvature at point B is defined in the same way, and it will be related to point A. In a simple medium, where the index of refraction is a constant, this is a very simple exercise to work through. If you move forward to point B, the radii of curvature is now 1 over rho sub 1 plus s and rho sub 2 plus s. Which makes sense, right? We're going that much further, so we now have to go back rho sub 1 plus s and rho sub 2 plus s to calculate that radii of curvature if we have a medium with straight rays. If we don't have a medium with straight rays, the amplitude function gets a little more complicated. I actually have to go back and calculate those integrals, the one that we had on the previous page. This one here, the Gaussian curvature integral. I would have to numerically integrate that. Now, let's do an example to drive this home. In a simple medium, demonstrate that the integral of the Gaussian curvature represents the ratio of Gaussian curvatures of an iconal surface of points A and B in a simple medium. So we're going to go ahead and prove that mathematically, that that's what that integral actually means in a simple medium. And to do that, we're going to do a little bit of change of coordinate system. If I have a gradient of a vector, normally I take partial derivative with respect to x along the x, and I dot that with my principal vector, and then I take partial derivative with respect to y, stick it on the y, dot that, project that onto t, that differential operator, and likewise partial derivative with respect to z. So I'm going to go ahead and change the coordinate system. Instead of decomposing this with respect to x hat, y hat, and z hat, we're going to decompose this with respect to t, u, and v. And the significant part of that is going to be if t hat represents my ray tracing unit vector, which we know is the gradient of the iconal over the magnitude of said gradient, which we also know to be the gradient of iconal over the index of refraction, then the t direction is going to be continued in the direction of a ray trajectory. U and v are going to be unit vectors that are perpendicular to that trajectory. So I'm just going to take the derivative, the partial derivative that projects in that direction, the partial derivative that projects in the u and the v, the perpendicular directions that should lie along the surface of the iconal. Okay, when I do that, here's what I get. The gradient, or the divergence of t, is really the divergence of the gradient of the iconal over n. And of course, we know this to be the Laplacian. So let's go back up at the top here and look at this equation again to see how we can evaluate this. First of all, the gradient of t, our unit vector, in the t direction is 0. It doesn't change its length for slight displacements, for slight advances of s. The gradient of t as I move along the surface with respect to the directions u and v are my Gaussian curvature radii. So this integral really evaluates to 0 plus 1 over rho sub 1 plus s prime which will be my variable of integration, and then 1 over rho sub 2 plus s prime. If these are the radii of curvature that correspond to the directions of u and v along the surface, which means this whole integral can be written as these two integral products. These integral forms are logarithmic in nature, so I have minus the log rho sub 1 plus s prime evaluated from my starting point to a distance advanced s. And this has identical form. The one in the orthogonal direction has the identical form. Conveniently, exb to the minus log is just whatever is inside there. So what I evaluate to, of course I have a minus sign so I have to flip it, what I evaluate to is starting condition rho sub 1 and rho sub 2, my initial radii of curvature, to my subsequent radii of curvature, which should be rho sub 1 plus s, rho sub 2 plus s. So this gives us a nice confirmation of the value or the geometrical definition of Gaussian curvature. In fact, here's our final solution. This is what rays look like in free space or any simple medium. We have a starting amplitude, and it could be an amplitude and a phase. It's just a constant here, E naught. If I want to construct my complementary magnetic field solution, I do the exact same thing. I've got E naught over impedance, which you'll remember from the review lectures, is square root of mu over epsilon. I have a polarization vector I can throw in here, and I just have to make sure that I get the perpendicular T cross E vector for my magnetic field. My phase term is going to be exb to the minus j. We had a k naught index of refraction times distance traveled. And of course, we've just joined these together as is common and called that the wave number of the medium in electromagnetics. That's 2 pi over lambda. And then here I've got my terms due to the Gaussian curvature. My starting curvature over my ending curvature. And this is in a simple medium. So a lot of math just to get something that hopefully you've got a little bit of intuitive understanding behind, but it's nice to see it all worked out. And this general solution that we have is actually quite useful. Let's go ahead and take a look at some canonical wave types. Canonical wave types are ones that you've probably studied in classes before. You've got plane waves, spherical waves, cylindrical waves. And of course the geometry of these waves is determined by its equiphase or iconal surfaces. In a plane waves, all the equiphase surfaces are planes, so we call them plane waves. In a spherical wave, all the equiphase surfaces are spheres, so we call them spherical waves. In the cylindrical wave, we have a bunch of waves that are cylinders, a bunch of iconal or equiphase surfaces that are cylinders. And if we actually look and calculate Gaussian curvatures, ask ourselves, what is the Laplacian of S over the index of refraction, that Gaussian curvature term in our equations? Well, for the plane wave, it's going to be 0. S is a plane, and when I take the Laplacian of that, I get 0, which means I start out with a certain field amplitude, and I advance in space from a starting point, S naught, in a particular direction. In this case, it's going to be the x direction, but it could be any direction. My path loss is going to be 1. I'm not going to lose any field strength or power density in this plane wave. If I did my pointing vector calculation, I'd find it would be a constant no matter where I was in space. In the cylindrical wave, we have a different situation. The Laplacian evaluates to 1 over rho, where of course we're using the electrical engineering rho, that is the distance from the z-axis. And the path loss is going to be related to whatever your starting point is divided by the point that you've advanced along a ray at distance s. Laplacian of the iconal of a spherical wave, if I actually do the math and plug it in, my amplitude should be E0 E diamond over R, 2 over R. And the path loss with respect to my starting point should be S0 squared over S squared. So whatever my amplitude is, or my power at the starting point, however long I advance on the ray, it's the ratio of the squares. And these are wave types that you've probably dealt with in one form or another in a previous class. But this is how we formally define them, using geometrical optics. Now it's important to note that these are all special cases of the special case of a simple medium propagation. If you have spatial variation in your index of refraction, of course the waves will start to bend, and you have to numerically evaluate that amplitude condition. Even in free space, these are special cases. So in ray optics, we have these things called astigmatisms. An astigmatic ray solution is not unlike the general case that I showed on the previous screen, where your radii of curvature can be irregular in two directions. Rho sub 1 in one direction, rho sub 2 in another direction. And astigmatic rays are the most general case in a simple medium. They're particularly useful for doing things like the geometrical theory of diffraction, which we'll study. It gives you a really nice tool for handling diffraction problems. Or GTD for short. GTD says basically, okay, I have a transmitter, and I'm sending out a wave or a source of some sort. Let's say I encounter a corner. Well, we know that in the far field, all sources ultimately act like spherical waves, right? Which means the radii of curvature at any given point is going to be the distance traveled from transmitter to that point in both directions. So 1 over r in one direction for curvature, 1 over r in the other direction, 1 over r squared for the total two-dimensional Gaussian curvature. And that's textbook that you've learned even in your sophomore physics class. When that wave strikes the corner here, though, one way to solve this solution is to add a GTD diffracted wave, which says that this corner acts like a localized source. So if you have a corner in 3 dimensions, that's really a line source. And that means that for this geometrical wave, one of the radii of curvature at that point is going to be 0, and it's going to start as you trace out the diffracted wave. You'll start to decrease the curvature, increase the radii of curvature in that direction. However, if you look at this problem from the side view, here's my edge, here's my source. In this direction, the radii of curvature doesn't change at all, which means by necessity this wave coming off this edge is going to be astigmatic with mismatching rho sub 1s and rho sub 2s. So an important thing to keep in mind. The world isn't only plane waves and spherical waves, despite what professors give the illusion or the impression of. And in fact, we'll be finishing up our ray lectures by studying reflections and also curved surfaces, which can also produce astigmatic rays.